This is the Advanced Extension Award from 2023. Let's just get straight into it. Cos is repetitive every 360, as we know, so just take away 360 from that to get cos 45, and it's the same thing, which is 1 over root 2. And now use the double angle, or otherwise, I guess I use the compound formula. I guess it's the same thing, isn't it? Start with cos 405, because you know cos 405 is 1 over root 2, and just say that it's these two things added together, obviously. And now using the compound formula, cos is the one that goes cos minus sine. So that's just cos squared minus sine squared. But sine squared is 1 minus cos squared. So you can write it like this, and most of you will recognize this as the double angle formula for cos when you're trying to keep it in terms of cos. So that's fine. And now, of course, we can kind of just do that again to get all the way down to 101.25. So I'm just going to do it again. I'm going to skip this line here, just jump straight from here down to the 2 cos thing minus 1 version of it, which is this. And then, of course, it's just a case of rearranging for cos 101.25. So maybe just add 1 to both sides. I'm not sure what I've done here, not really a lot at all. Just add 1 to both sides, and then this has got a rational denominator, I guess. Let's maybe rationalize this first. So bring it together, then rationalize like this. Now we can divide by 2, and then I can square root. Now when I square root, I'm going to square root the 4 down to a 2, and just square root the top here. Now how do I know whether it's a plus or a minus? It's not both. It's one or the other. Well, cos 101.25. Now that's, if you imagine the cos graph, it starts at 1, goes down to 0 at 90, and then continues heading downwards, right? So cos 101.25, the size of that is less than the size of 120, which I know to be like a half. So when I square this, it's going to become positive. It's a negative number right now, but that's okay. When you square it, it becomes positive. But it's definitely less than a quarter when you square it. And then when you times by 2, that makes it less than a half. And then we take away 1, it's definitely negative. So I think this is definitely a negative number. So I'm going to use the negative version of it. I'm going to add 1 to both sides, then divide by 2 again. Okay, first I'm going to put these together, and then I'm going to divide by 2, I guess, and then I'm going to square root again. Now, we've already discussed that cos of 101.25 is definitely negative. So we'll take the negative version of that, not the positive one, and then we'll just write it in the exact form they wanted it, I guess. And we'll have our answer with A being minus half, B being 2, and C being minus 1, I guess. And everything else matches up. This person is doing a proof that there are an infinite number of primes. Okay, it's not a very good proof because it doesn't work. Because if you start with p equals 7 and you assume that's the last prime in your list, so his primes are 2, 3, 5, and 7, then you get to 15, which isn't prime, it's 3 times 5. It's just a product of 2 of the primes in your list. So his proof doesn't work. It also doesn't work if you change it to 6p plus 1. It takes a little while to find. It's annoying, but eventually you find 19 breaks it because you get to a multiple of 5. So that doesn't work either, even with that fix. And then it says write out a proof by contradiction for this. Now this is this is Euclid's proof, which basically you just say your list of primes is P1 to Pn. This is not going to be proper. I'm not going to do this properly because I've done this so many times in so many classes. Just find a video on Euclid's proof of an infinite number of primes, and you'll explain it properly. I just wrote down a very rough draft of it. You calculate the product of all the primes in your list. That number is obviously not prime, but if you add 1 to it, it's definitely not divisible by any of the primes in your list. So therefore, because it's got a remainder 1 with all of them, so therefore it's either prime or it's the product of 2 primes that weren't on your list. In either case, more primes have been found, so there's a contradiction to the fact that you originally stated that you've got a finite number of primes, which is this list here. So yeah, that's the contradiction, and you can just repeat that argument over and over again. Once you found new primes, you can just multiply them all together and find more primes, and so on and so on and so on. Well, actually, not really finding more primes necessarily, but you're at least deducing that there must be some. Okay, the next one is about some integration, which is nice. Determine the value of t. So we're just looking for the intersection between this curve and this one here. Now this is a circle radius. This at the origin, so that's x plus y squared is this thing squared, which is 25 times 2 over 4, which is that. So now let's just put that guy, or let's just put these two values into here, I guess, to find the value of t. So this goes in there and this goes in there. I've just squared them out. This makes a quadratic in sine and cos. So let's just make it one of them by replacing that with a 1 minus cos squared. And then you just do some very boring maths. You cancel some stuff down, you times up to make more stuff go away. You end up with the quadratic, as we were talking about, which you factorize. This doesn't have any solutions, this part here, because you're looking for cos to be bigger than 1. This is cos needs to be a half, which is fine. You've got 2 values of t that will do that in this range. You've got pi over 3, I believe, is the first one, and then 2 pi minus pi over 3, thinking about the symmetry of the cos graph that I've got in my head here, which I couldn't be bothered to draw. 2 pi minus pi over 3 is this. So those would be our two t values. Now, which one is the one for the point at B? Well, B has a positive x coordinate and a positive y coordinate. If you put sine of 5 pi over 3 in here, you'll get a negative number because sine is the one that goes up, and then it's negative for all of the second half. So this has got to be the pi over 3 version. So t is pi over 3, I think is the right answer. And then we want the region R, which is all of this stuff. We want the area of that. So I came up with a plan for this, which was cut it here and work out this little sector by just working out this angle and then this radius, and fine. Then integrate the curve, this bottom curve between here and here, and then work out this triangle, and then if you put some things together, you should end up with R. Of course, you're also going to need times by 2. So the first thing was work out B. Well, we know what happens when t is pi over 3. Just put pi over 3 in here, and you'll get 5 over 2, 5 over 2. In case it hasn't been clear, when you're doing advanced extension award, you must know all of your exact values. So sine pi over 3 is root 3 over 2, so you get this, and then likewise with cos is a half, so you end up getting this here. Anyway, that means that this angle is pi over 4 because it makes an an isosceles triangle. And this is the line y equals x, it turns out. So this angle here is also pi over 4, which means this sector here, I'm going to say, if we first just focus on the right-hand side, which is a half of r, right? A half of r, this right-hand side here, is the sector plus the triangle underneath, which is just a half times pi over 2 times 5 over 2, minus the integral underneath this curve here, which I'll just say minus the integral. This, by the way, is just, of course, an eighth is pi over 4 is an eighth of a circle, so an eighth into pi r squared. This is 5 over 2 root 2 because I'm imagining the 1 root 2 triangle in my head, and then you just multiply it up to 5 over 2, 5 over 2, 5 over 2 root 2. So that's the hypotenuse of that. Now the integral then is the next thing we need to work out. I also just doubled this whole thing, I guess, and did some rough calculations in here to get this. Now the integral then. So the integral is going to be the integral of y dx, except I can't really do that because y is in terms of t. So I'm instead going to integrate y dx by dt, because the t's would cancel and you just end up with y dx, except they're not going to cancel because everything's in terms of t. So now we just throw y in, we throw dx by dt in, which is just 5 over 3 cos t, so that was nice and easy. And then we just have the dt at the end. Can't calculate this, which is that. There's tons of ways to integrate cos squared, but probably the most used way is to use the same double angle formula we saw earlier and just rearrange it for cos squared, which is going to be what? Cos 2t plus 1 all over 2, or a half of each thing. They're both minus because we're taking away the whole thing at the end anyway. And we just integrate this. The good news is that sine is 0 at 0, and so is t. So all of the second interval just goes away. I pulled out the constants, by the way, because I didn't need them. And then, of course, we just end up putting the numbers in. Again, knowing exact values helps a lot here. Knowing what sine 2 pi over 3 is, for instance, for example, to get you this. And then that equals this. And then we just use that inline integral here by timesing by 2. And the region is this. I think I didn't even bother simplifying this because it didn't actually tell me to. So I'm hoping this is worth full marks. It's a risky way of doing it, but I'm hoping that this technically fulfills the criteria of the question. If I were you, I would probably spend 30 seconds actually bothering to simplify that, but I couldn't be bothered to do so. You do get a formula book in Advanced Extension Awards, so I'm just going to put this down here, and I'm just going to use it. So h is b over a, b minus a over n. N is 4, b is 1, and a is 0, so that's 1 minus 0 over 4, which is a quarter. So h is a quarter. These y's are just the value of the function at the certain points. So y0 is at the start, so that's 16 to the power 0. Yn is the function at the end, so that's 16 to the power 1. So those are the first two values. And then these are all the middle ones. So if you're breaking the thing into 4 strips, you're going to have 0, a quarter, half, 3/4, and 1. Those would be your strips here. So that's just all the powers up there. So those are the y values at those points. Just type that in a calculator and hopefully you'll get that. To give an expression for it, well, you just use the expression in the formula book. And I guess I could have simplified this, but again, it didn't actually tell me to. I guess I could have written 1 over 2n into 17 plus this, but I did write that. Okay. Yeah, it didn't really tell me to though. So oh no, I think I'm now doing part C. Yeah, I'm now doing part C. Anyway, I've simplified that, so that's so I guess I've done it as part of both questions. Hence, show that the integral is this thing here. Now, this is what happens when the integral is the trapezium rule as long as you use an infinite number of strips, right? That's kind of what integration is. So we can just say that this equals this thing here as long as n is going towards infinity, and I've simplified this thing up here as I was doing it. But this is okay because what I'll do is I'll just break 17 and down into 15 and 2, and that means I can throw this 2 into this bracket as long as I turn it to a 1, because now 2 times 1 is 2, and that's that one there, and then the rest of it goes on. But now I can I can expand this out to be this, and then break this limit into the limit of this bit plus the limit of this bit. But of course, the limit of this bit is just 0 because you're sending n to infinity, so this is just going to go away. And you'll be left with the thing that they wanted you to get, which is this thing over here. Kind of ran out of space as I was writing this, apologies, but you get the point. We end up with the thing that we were supposed to get. Now it says use some integration to find this. This is the easiest part of the question by far, as long as you know how to integrate things like 16 to the power x. When I say log, I mean log to base e, obviously. I know that's confusing, but I also don't care. Then you put in 1 and 0, and you obviously just get 16 minus 1, which is 15. And that's the exact value. And then it says, given the limit exists, use part C to determine the exact value of this here. So we need to use both parts, obviously. Now we can say that, of course, part C says this thing equals this thing, but we know this thing equals this, so this can therefore equal this thing here. And now, okay, let's work with this. Well, this here is just a sum. It's just a geometric series, isn't it? It starts at 1. Every single time we go across, you times by 16 to the power 1 over n, I guess, because this is like 16 to the power 1 over n squared, and this is 16 to the power 1 over n cubed, and so on. N is just, there are n terms because it starts at 0, 1, 2, 3, all the way to n minus 1. It means there are n minus 1 terms here, I guess, with an nth there, you could think of it as. So anyway, we use the formula, which is this, and we put that in. 16 to the power 1 over n to the power n is just 16, which is very nice of it. And that becomes a 15, which is really nice because then it can cancel with that 15. And now this is kind of getting somewhere. As long as you make this nice little substitution to actually get this limit to come out of it. Because, of course, when n goes to infinity, x is going to go to 0 here. And then this just becomes an x, and this just becomes an x, which is very helpful. So you get this, which is still equals this thing over here. And now this is just upside down. So even with a limit here, we're still allowed to just flip this over and to say log 16 over 1 is the same as the limit as x goes to 0 of this thing flipped over, which is what they wanted me to talk about. So that equals log 16 just there. Question 5 then is the stats question, so we know that I already hate it, but it's the kind of stats that's not that awful, so I guess I can deal with it. P of f is just all of these things added together over n, and that equals 3/7. Apparently, n is the total of all this. I could have written out all of this added together, but I couldn't be bothered. H given G, so that's the things in H and G over just G. So that's A plus C over A plus B plus C plus 5, and that's equal to a third. F is independent. Independent means f of A times f of B equals the intersection of f of A and B. Was I saying f of A and f of B? I mean P of A and P of B. F just being the probability function, I guess, and that's fine. Anyway, this is the condition for independence. So if f of is independent of this, that means P of f times P of H and G is equal to P of f and H and G, I guess we can say. So therefore, this here is P of f, because it's the things in f over the total, times the things in H and G, which is just A and C over the total, is equal to the probability of f and H and G, which is just A over the total, because that's f and H and G. So this is just saying probability of f times probability of H and G is equal to probability of f and H and G, because they're independent. Okay, so that's all fine. Show that this thing here, well, this thing here is just A over n, as we've already discussed. The intersection of all three is just A, so that's A over n. But that's equal to this thing here, based on what I just said. And this thing here is quite easy to deal with because you know this bit is just 3/7. Just all of this is just 3/7. I didn't need all of these letters as I was going along, but it kind of helpful for later, so I just left it. And this thing here, well, A plus C is just this thing over 3. So I can replace that with A plus C, just cross multiplying that over and shoving it in. And then, of course, well, the 3's cancel, and you just end up with this over 7n. which is the same as a seventh into that. But just notice that thing there is, of course, just 5 plus A plus B plus C. That's just G. So this is just the probability of G. It's the things in G over the total. So that's 1/7 probability of G. Again, you didn't need all these letters when you were doing that, but they're useful for later. I think I remember them being useful for later, so I just left them. Prove that if X and Y are independent, then X dash and Y dash are also independent. I think this is just proved in the textbook, if I'm not mistaken. Again, this is the condition for independence. So what I did was I started with this and said, okay, yeah, sure. Then we can just say, well, P of X dash is 1 minus P of X, right? Expand that out. And now if we look in the Venn diagram, sorry, by independence, it says if X and Y are independent. Well, if X and Y are independent, then P of X, P of Y is P of X and Y. So I can use that step. Now looking in the Venn diagram, P of Y, which is this circle, minus the intersection of X and Y, well, that's this crescent here, which can be written as P of X dash intersected with Y, right? It's the things that are both not X and Y. That's this crescent here. But of course, now we have a chain that goes this equals this, so therefore those two things are independent. And I think that'll do. For C, hence find this thing here. Well, if we return to our numbers a little for a second, we can use the independence idea because we're told F is independent of H and G. By this idea here, that means not F is also independent to H and G. So we can say that this thing here is equal to P of F dashed times P of F of H and G. P of H. I keep bringing random F's in my sentences. I'm not really sure what I'm doing. But anyway, it's the story of my life. So yeah, we're now just using this idea to break this down into this. Now, what things do we know here? Well, just like before, we know P of F dashed is 1 minus P of F. We know P of F is 3/7, so that's going to turn out to be useful. And we also know the probability of H and G is just A plus C over the total, which is N. So that's going to be helpful as well, because we know that A plus C, as we saw before, was just this stuff over 3N, I guess, because the N just carried on from down there. And of course, we can just do the same thing we did before. This is 4/7, bring out the third here, and then this is just the probability of G when you get rid of the third, because those are the things in G. So we end up with 4/21 G. Show that C is that thing there. So okay, well, all we have to do here is go all the way down here and say A of N is equal to 1/7 of P, and now I've written out P of G properly here, just there. But now we can also use the result we had before up here. Now, what is P of F dashed and H and G? Well, that's just not F in H in G. Well, that's just C. So that's just C of N. So this says C of N is 4/21 of that same thing. And now we could, I've just spotted there's a much easier way of doing this than what I did, but who really cares? I cross-multiplied this and cancelled the ends at the same time because I'm a muppet. And then I cross-multiplied this and cancelled the ends at the same time. Then I think I times this by 4 and then just threw this result into here because we've got the same thing now to get this, which turns out to be this. You could, I guess, have just said 21C over 4N is equal to this and just put it straight in there and then cancelled some more things. It doesn't really matter, does it? We get this in the end. Given further, the probability of F given H is 1/5. Well, the probability of F given H is D plus A over A plus D plus C plus 16. So okay, that's apparently equal to 1/5. Find an expression for D in terms of A. Well, that should be fine because I can just replace C with 4/3 A and cross multiply, and then I just have things in A's and D's. So that's very easy for me to work out. So we end up with this. I guess I probably should have, before I run off this line, should have written D equals 48 minus 8A over all over 12, I guess, but whatever. Just imagine I wrote that here. And then it says determine the maximum value of A. Well, 12D is bigger root to 0. So therefore we can just say that because these are non-negative integers. And then we can just say A is therefore greater than root to 6. Sorry, less than root to 6. Just remove that over, divide by 6, and you end up with that there. Then it says determine the possible values of N. Now, what we need to do to even make a start here is realize that this is a very restrictive condition when also combined with this here. And also combined with this here. Because they're all non-negative integers. And because C therefore is an integer and is 4/3 of A, that means A has to be a multiple of 3. And the only multiples of 3 that meet this condition are 0, 3, and 6. So A has to be 0, 3, or 6. And so now we just need to set A as either 0, 3, or 6, run through the maths and find what N would have to be in each case, And those are possible values of n. So firstly, if a was 0, that would make c 0, of course. And it would also make p of g 0, because both of these are 0. Because of this, right? If a was 0, the probability of this would be 0, because a is that. And then that's 1/7 of 0, therefore. So p of g is 0, but that makes b 0. And the entire thing just becomes... I mean, p of g can't be 0 because of this 5, right? So the whole thing just breaks down. So a can't be 0. So we'll get rid of that. We'll say a is 3 instead, which makes c 4. And then we just have to use the rules that we wrote down earlier. So this, we can start with this one, I guess. This, remember, was a over n, which I now know to be 3 over n, is equal to 1/7 p of g, which is just all these guys added up over n. So this should really say an a, because I haven't put the other numbers in yet, but that's fine. Now we can put the other numbers in, cancel the n's, of course, we don't really need them. And we can solve for b. We get b is 9. And then we can also use this rule up here that we got given halfway through the question. Remember, we said f given h was just a and d over just the h circle. So that's this equals 1/5. But we now know, in this case, a is 3, c is 4, and d is 9. Sorry, b is... I'm not even using b yet. Cool, fine. We don't need b. We can do them separately. We can just solve this for d. And we get d is 2. And then we can finally go to where are we getting this expression from? P of f. P of f is just these things added together equals 3/7. And that will give us n, because we know a is 3 in this case, b is 9, and d is 2. So that will give us, times this by 12, I guess, we get n is 84. So okay, n is 84 in that case. Then we just do this exactly the same thing with a equals 6. I just copy pasted the slides here, so I don't need to talk about this. It's the same thing. And you actually end up with n is 119, and that's all good to go. For question 6, then, a nice, easy... It is a very long question, but it is nice and straightforward just because it's a lot of calculus and stuff. First thing we're going to show with this thing here, well, if the volume is this, we've got a bit of a complicated thing to do with this frustrum here, but that's okay. The volume of the hemisphere is obviously just half of this expression there. So we've got 2,100 pi is equal to half of this expression here with big R, because that's the radius of the hemisphere. Then we need to plus kind of this entire cone that we can imagine going all the way to the top. And now, because this is 2r across and this is r across, that means that this is halfway up the cone. So therefore, the height of the kind of imaginary whole cone is 8r, because this is just halfway up it. So that means we get this expression. So we'll add in the entire fake cone. And then, of course, we're going to remove the half cone that we made up, which has height 4r, radius little r. So that's all of that. And then, of course, if you just do some maths, it ends up working out pretty well for you. And you end up with this, which is fine. And this is express dr by dr, d big R by d little r. And now it says in terms of r and big R, which is really helpful because it means we can do some implicit differentiation. We can just differentiate both sides to say this is 3r squared d big R by dr, and then just differentiate the side and then just divide by 3r squared. And cool, it's much easier than any other way of doing that. The base is fixed to the ground, so we're going to work out the surface area of this, obviously without this made-up cone. Work out the surface area of this without the basey bit down there is our next job. So okay, let's do that. Well, the obvious bits to do are the surface area of the hemisphere first, which is just half of this value there. So that's fine. Also obvious is this bit sort of under here is just pi big R squared minus pi little r squared. And now the more complicated bit is the surface area of this cone here, which we again need to do the idea of, well, just work out the surface area of the entire cone using a height of 8r and a radius of 2r, which is this here, and then take away the little cone, which is radius r, height 4r, which is just there. And now when you put the maths together, you get this. You can say root r squared, but in both of these is just r, so that turns this into an r squared. And also, very helpfully, root 68 is, well, 68 is 4 times 17, which is very helpful because that makes it simplify down to 2 root 17. So everything just becomes this, and then you can group together the things that you want to group together, and you actually end up with the answer that they wanted you to get, which is great. I'm going to leave all that stuff at the top while we plow on with the rest of the question, which says, hence show this thing here. So we're going to differentiate this. And again, implicit differentiation is going to be helpful here. So we're going to differentiate with respect to little r. But big R, I'm just going to say big R squared differentiates to 2 big R times d big R by d little r. Right, so that's just more implicit differentiation there. And then this is just differentiated normally because it's already in terms of little r. But now we can just replace this d big R by d little r result that we found earlier in here. And we should be good to go. And we'll get this here. And so alpha, or sorry, gamma, it looks like, is just this mess here, and then delta is like this thing here. So that's all fine, good to go. Now we apparently got a minimum point here, a maximum point here, and then I think this is called a cusp, I think, here. Determine the coordinate of that. Well, the only thing that's going to go wrong with working out this gradient function ever is when big R is 0. So that happens when big R is 0, but now we can just go back to here and say, well, if big R was 0, little r is just this cube rooted over 14. And yeah, so that's when that happens. Explain why this must be, why little r must be less than that. Well, again, if it was more than that, then that would make big R negative. And so you can't do that because big R is a volume, sorry, is a radius, is a length, right? So yeah, can't do that. Okay, the last part, show that our coordinate of m is this thing here. So this looks fun. So of course all we have to do is set the derivative to 0 because m is a turning point. So we take this derivative here and we set it to 0. Now r equals 0, it's already told us as an answer to this. It says there's a minimum, sorry, there's a maximum there, apparently. No, minimum, sorry, at r equals 0. So okay, r equals 0 is fine. We're allowed to divide by r equals 0 because it's told us it's a known minimum. We can also, I guess, just divide everything by 2 just for simplicity, and by pi, that also helps. Now just rearrange for r. Except when you rearrange for r, this is a little bit more difficult because you need to get rid of this big R somehow. The only formula you have for big R is big R cubed. But you look at the answer, always keeping your eye on the answer, and you notice that's also in terms of cubing things. So let's just cube everything and feel quite safe that we're not only getting to a better place in terms of putting this result in, but also looking at a bit more like the answer now. So that's fantastic. So now we put this result in, cross multiply, I guess, expand this out, don't expand this out, don't need to. Just expand this bit out and then just move everything over. So I just put this into here to make this, put this in here, but then took it away from both sides, or added it into both sides, I should say, before factorizing out the r cubed. And now we're pretty much there, right? Because all I need to do is divide by this guy here, which looks a lot like this, and cube root, and we'll be done. Now, these numbers don't look quite right. There's no 14 here, so I think what we can do is just divide everything by 14 and get out a bus stop to figure out what this is. And now when you divide this by 14, obviously this divided by 14, it just goes away. When you divide this by 14, this is 42 times 42 times 42. You only need to divide one of those 42s by 14, which becomes a 3. So this becomes 42 times 42 times 3, which is 42 squared times 3, which is now where this is going to come from. Q is 42, and P is whatever that is, which I believe is 225. Okay, just divide the cube root, and we end up with our answer. And that's that one done as well. And now we have finally a nice little sequence question that just has some algebra at the end to do. So, okay, we're asked first that the sequence is constant. Now, if one of the terms of the sequence is A, that means they all are if the sequence is constant. So that means it just goes A, which means that A is equal to P plus Q over A, because every term is A. And we can just rearrange that, and we'll get Q as this thing here. So that's the expression for Q such that it's constant. Now, what value of P is necessary for the sequence to have order 2? If it has order 2, then it goes A into not A, into A, into not A, into A, into not A, and so on. So what that means is, for any term in the sequence, A is equal to P plus Q over not A. But then also, via the next term, not A is equal to P plus Q over A. So we can shove that result into here to get a result in just A, P, and Q. And then we can try and rearrange this to figure out some necessary condition. So I'm just going to times everything by P plus Q over A, I think. Or I'm just going to put it into one denominator first, I guess, and then times by it. Sure, that works too, I guess. These A's will cancel straight away, which is nice. That's probably why I did that. And this just turns into this. And now this is kind of cool. So what we're going to do is we're going to obviously cancel the Q's. That seems kind of helpful. But what we can say here is that if we divide by P, now we know P equals 0 is one of the solutions to this, right? P equals 0 would just solve this straight away. So let's note that P equals 0 is a solution and divide by it. We are left with this. But look at how this is actually the same condition we found earlier for a constant sequence. And that's, of course, because I never said at this point that A dashed had to be uniquely different to A. So this is also just happening to describe a constant sequence if the two things are the same. And that's what I've got here. So what we're saying here is it's necessary for P to be 0 to have order 2, because the only other way you can do it is by having the thing be constant, which is technically order 2, I guess, but we've already described that as being order 1. So I guess we just need to leave that there and say p equals 0 is therefore the necessary condition, because the other thing just makes it constant. Now, it's not sufficient, which is what it's saying here. Give an example of a sequence that satisfies p is 0, but not order 2. You can just say the first time is 1, p is 0 and q is 1, and then you just get 1 equals 1 over 1, which is 1, and then you get 1 equals 1 over 1, which is still 1, and you make a constant sequence. So that's what I'm saying. Essentially, you're meeting this condition as well, and this one apparently matters more. So yeah, necessary but not sufficient, I guess. Determine an equation for q such the sequence has period 4. So yeah, you knew that's where this was going the whole time. So this is a sequence that goes the first term, second term, third term, fourth term, and then the fifth term is the same as the first term, so it's order 4. So okay, that means that I guess we can say A2 is P plus Q over A1. And then we can say A3 is P plus Q over A2. But the thing is, like, if you know that A2 is P plus Q over A1, you can put that result in there. And then you can say A4 is P plus Q over A3, but you know A3 is this result here, so you can put that in there as well. But then you know A5 is P plus Q over A4. You know what A4 is, you can put that in. But you also know the fifth term is supposed to be equal to the first term. So now you've got both things in terms of A1. And all we have to do is try and figure out what this is going to give us in the end. So it's a lot of algebra. I'm going to get rid of the A1s and just write A's because in PowerPoint it's easier. So at this point, just pretend A1 is A. But okay, what I'm going to do is times everything here by the blue term, which gives me this. And then I'm going to expand out a little bit. So this is just AP plus AQ over that same thing, P squared plus PQ over that same thing, plus Q. And I'm going to do that again, just times everything by this whole denominator that's appearing twice here to get this. And then again, expand out. So just expand every time out here. You get this. And then once again, just times by P plus Q over A everywhere. You get this. Expand out. You get this. You just need to pray to whatever God you believe in that a lot of cancelling is going to happen. It sort of does. It's not as much as you'd like, but there is some cancelling here. There's also some combining of terms, which is nice. So some of these terms combine, so you can do that as well. Eventually you end up with this. You can check the maths if you'd like to. I think I times everything by A here just because I didn't like the fractions. So that's fine. And now every term has a P in it. So remember we said order 2 meant a necessary condition with P is 0. Now in the same way that anything that's order 2, anything that's order 1 is technically order 2. It's just where the two terms are equal to each other. Anything that's order 4 or anything that's order 2 is technically order 4 because you could just pretend that the terms are different to each other. Like the sequence 1, 2, 3, 4, 1. Sorry, the sequence 1, 2, 1, 2, 1, 2. You could pretend is order 4 because you can say it's 1, 2, 1, 2, and then 1, 2, 1, 2. It's repeating every 4 things. Well, yeah, sort of. So P equals 0 is the condition for order 2. So it's not surprising that it turns up again in order 4, and we can just divide by it and say, well, actually, we really want order 4, so we don't care about the P equals 0 case, because that's just going to give us order 2. So let's just divide by that to get rid of it. And then likewise, if you arrange to make 0, you can make the same logic where you can say, okay, well, remember the condition we saw earlier for order 1? That condition should turn up here, because again, anything that's order 1, you could technically call order 4. So this condition here should turn up here, just like the condition for order 2 turned up here, that being P equals 0, obviously makes all of this work. So I think that this condition here should turn up in this. I've rearranged this, by the way, to make a cubic in P, just because I wanted to. Now we can rearrange this for 0. And what we can say, therefore, I guess, I think I just times this by -1, is that this term here should be a solution to this. Because again, anything that we've set as order 4, the order 1 condition should come out of it. Because at no point in any of my A1, A2, A3, A4 answers, at no point in any of that did I say that they had to be different. If they're all the same, this is just order 1. So therefore, the order 1 condition should fall out of this. So that condition here, this thing here, should be in here. So that's exactly what I did. I just said, okay, well, let's open up a bracket and just say that this condition here, that thing equals 0 for an order 1. Let's just say that that should be it. Well, what if it is? Well, okay, well, what do we have to multiply this by to get back here? Well, AP times P squared is AP cubed. and q minus a squared times by 2q is, I think, precisely this. So we can just have a plus 2q here, and then all of this times this is just all of that. How do we make our p squared and p terms? Well, actually notice that q minus a squared times p squared is just this, right? So I think I need no more p squared terms. And just check this with the p term. Um, well, okay, currently we have zero, sorry, from the p's. We have two aq p's here, and zero of them anywhere else, which is fantastic, because that's exactly what we wanted. So therefore, this is a condition, remember that gave us order 1, but also this is a condition whereby p squared equals minus 2q, or 2q equals minus p squared, I guess we could say. So q is minus half p squared, I guess is what we'll say there.